Magnetism. So the second half of this course is electricity and magnetism. Turns out that the electromagnetic spectrum, electricity and magnetism are related to each other. You don't have the flow of electrons without creating a magnetic field. And when you have a magnetic field, you create the flow of electrons. That's how a power plant works. It rotates around a magnet inside wires and creates the flow of electrons. That's what goes on when you generate electrical power. We have all sorts of examples that we can see in nature of electricity and magnetism. It turns out that in the upper atmosphere, well, anywhere in our atmosphere, we have about 1,000 charged particles per cubic centimeter, positive charges and negative charges, just because some molecules tend to happily associate some extra electrons or give up an electron and be ionized particles. And so we'll sometimes have a deionizer in a room or something to try to eat up the free radicals and do stuff to the charged particles. Well, in the upper atmosphere, there's even more charged particles per cubic centimeter, and there's fewer things for those to collide with and neutralize. And so you get a case, the upper atmosphere, where the Earth's magnetic field and those charged particles interact, and as they're frictionally bumping up against the atmosphere and heating up and glowing, you get things like aurora borealis, or the northern lights, that you can see up in the sky. All sorts of things are not possible without understanding magnetism. Electricity and magnetism are tied together. Magnets come in all sorts of shapes and sizes, and I think we're used to sticking something to our refrigerator that's a permanent bar magnet. It's a magnetically charged piece of ferromagnetic material that will hang out somewhere. If we have a magnet, it has a positive or a northern part and a negative part. It's kind of originates in our understanding of geography. So the Earth's north geographic pole and south geographic pole, it's not actually straight up and straight down because the Earth is rotated on its axis, and it's even tilted from the axis of rotation, the magnetic field, and it behaves as though there isn't, but it behaves as though there is a giant bar magnet inside the Earth. And that giant bar magnet has a south magnetic pole near what we call the North Pole, North Geographic Pole, and a north magnetic pole down near where we call the South Geographic Pole. And those poles would attract a magnet that you held in your hand. The north part of your magnet in your compass would be attracted toward the south magnetic pole on the Earth, and so that's how we come up with those names. So this is incorrect. It should say south magnetic pole there, obviously. So the needle of a compass is a permanent magnet that has a north pole at one end and a south magnetic pole at the other end, and is attracted to the north and south pole of the Earth. So magnets behave similar to that of like and unlike electric charges. So if you've ever tried to force two north ends of a magnet together, you'll find that they repel each other. Two south ends of a magnet together, they repel each other, whereas north and south ends of a magnet attract each other, sometimes pretty strongly. We can look at magnetic field lines, just like electrical field lines, by taking some compasses and arranging them somewhere around a bar magnet. And we'll see that the north pole of our compass magnet is repelled from the north magnetic pole here and ultimately attracted to the south magnetic pole. So we can draw magnetic field lines just like we drew electrical field lines. and we can see what's going on there. This kind of looks like a capacitor, doesn't it? you can set up a bar magnet and shake iron filings, and those iron filings will be attracted to locate themselves according to the magnetic field lines. So there's our other view of the Earth. All right, so if we have electrical charges in the presence of a magnetic field, they will experience a force. That force, we'll see, this is our second right-hand rule. I think it's our second right-hand rule. The force is coming out of the palm of your hand. The magnetic field lines are your fingers of your right hand. And the component of the velocity that is perpendicular to the magnetic field lines is represented by your thumb. That is how you get the right-hand rule, to figure out the direction of the force that acts on a moving charge with some velocity inside a magnetic field. If the charge isn't moving, it won't experience a force. And this is, the assumption here is a positive charge. If the moving charge is negative, then it would be opposite. You'd be hitting it with the back of your right hand. Or you could do the left-hand rule. So the definition here, it's force equals QVB sine theta. Or if we're solving here, we're trying to define what magnetic field is. It's the force divided by Q, the quantity of charge, times velocity sine theta. If it's perpendicular, then sine of 90 degrees is 1. So it's force divided by QV. And so the units for magnetic field, Newton, seconds, coulomb, meter, is Tesla, 1 Tesla. And if you have 10 to the negative 4th Tesla, that is a Gauss. So sometimes you'll hear these different terms used. We'll be doing things in Tesla. So a proton in a particle accelerator has a speed of 5 times 10 to the 6 meters per second. The proton encounters a magnetic field whose magnitude is 0.4 Tesla and whose direction makes an angle of 30 degrees with respect to the proton's velocity. Find the magnitude and direction of the force on the proton, the acceleration of the proton, so force equals mass times acceleration. So we'll have to look up the mass of the proton. And what would happen with the force if it was an electron? Just be opposite. So first of all, force equals QVB sine theta. So that's typically the form of the equation we'll use. Q is the charge on the proton. Velocity we're given. B, the magnitude of the magnetic field we were given, sine 30, gives us the force. Acceleration equals force over mass. So the mass of a proton. So we get an acceleration. And then, the magnitude of the force is the same, but the acceleration is going to be different because the mass of an electron is different from the mass of a proton. So I guess I shouldn't have been so quick there. So it's the opposite of the force, but it's a different acceleration because it's a different mass. This is used in mass spectrometry. If you have a magnetic sector mass spectrometer, what you do is you shoot a charged particle into that magnetic field, and then you measure how much it's deflected by as it goes into that magnetic field. So you have to both know the velocity and the magnetic field strength, and then you have insight, just like we would have had here, into the mass of the particle. And if you can figure out the mass of the particle, then you have a great tool. Now here's another thing. We're doing stuff in 3 dimensions now, right? So remember when we talked about the right-hand rule? We have the force in one axis. Here I guess it's depicted as the y-axis. The magnetic field is in the x-axis, and then the velocity here would be in the z-axis. It's actually coming out perpendicular in the z-axis. So if we're going to do stuff in 3 dimensions, we have to have some way On a piece of paper, we have the y-axis, the x-axis nice and easy, but what about the z-axis? The z-axis we're going to represent with little x's. So here's a case where the magnetic field is going into the plane of the page. So we're showing like an arrow looking at the back side of the arrow with an X, as opposed to a case, where's a case where it's little dots? That's like looking at the head of an arrow coming up out of the page. So if we're going to represent 3 dimensions on a 2-dimensional space, we'll do it like that. The magnetic force always remains perpendicular to the velocity with our right-hand rule, and it's directed toward the center of a circular path. So we have centripetal force. Centripetal force equals mv squared over r. The force is qvb if sine theta is 90 degrees, if it's perpendicular. So force equals qvb equals mv squared over r. So r, the radius for something to go around in a circle here, r equals mv over qb. So we could inject a particle into a magnetic field and figure out its radius going around. That has applications in mass spectrometry. We won't do bubble chambers. Here's a case for figuring out the mass of a charge. So we take an ion source, we inject the ion into our magnetic field, and then depending where we place our detector will tell us the radius of curvature. And if we know the energy and the radius, the magnitude of the charge and the radius squared divided by 2 times the voltage, we're able to figure out the mass of that particle. So this is a mass spectrum showing the naturally occurring abundance of neon. We have a couple of mass specs in the chemistry department. It's a useful tool for figuring out what's going on with charged particles. Instead of doing force equals qvb sine theta, since q over t is current in amperes and velocity times time is length, we can do force equals ILB sine theta. And that would be a case where if I have a current carrying wire and it's carrying, I don't know, 2 amps of current through a magnetic field, and the cross-sectional area there, the length that this wire is traveling through the field is, I don't know, 1 meter, I could figure out what the force experienced by that wire would be inside that magnetic field. There's all sorts of applications here. You can have magnetohydrodynamics. If you have a source to hook up an electromagnet, then hook up your electromagnet and take seawater, which is a bunch of charges that are traveling, and so you can generate a force. Force equals qvb sine theta. So just by starting your magnetohydrodynamic boat moving, when the seawater travels through your induced magnetic field, it will create velocity, it will have a force, and it will propel you forward. It's pretty cool. All sorts of things here, right? So if I have a magnetic field and current traveling through a wire and I arrange it like so, then there's a force that's pushing on this wire. Now this is pretty significant because I can use electricity to light up a light bulb. But how do you take electricity and turn it into mechanical work? How do I take electricity and have a robot vacuum cleaner go around and clean up my house? I have to do something. I can have electricity turn it into light really easily, but how do I turn it into mechanical work? And you do this by way of a motor. And this motor has a shaft that will rotate around, and then somehow by gears and other mechanisms I'll have that do the work, making my robot vacuum cleaner roll around my house. But the wire here that goes through this thing is arranged such that in the magnetic field, when I run electrical current through the wire, it creates torque. It creates a force that will cause this to rotate around in a circle. And when I do that, then I have net torque and motor. And we don't need to get into the details here because it looks pretty hideous, right? I just want you to know that it exists. A motor, the other thing that you can have is an electrical generator. So the motor on one side, a generator on the other side. But that takes us to the fact that when you have current traveling through a wire, it's creating a magnetic field. So when we have a circular loop of wire, it's creating a magnetic field that we could measure or at least inspect. And what happens here is a case that if I hook up a current carrying wire, it creates a magnetic field. We call it a phantom bar magnet here. It's just creating a magnetic field lines. This is an electromagnet. So just by running current through a wire, I'm creating what behaves entirely like a magnetic field in space. Solenoid, bunch of coils of wire, run current through there. We have strong magnetic fields. We can do all sorts of electrical devices with that. Okay, I think that gives you what you need to do the Chapter 22 homework, and that takes us to the end. Good job. Make sure you can get through the homework. Look at the practice exam. You will be in good shape.